Okay, so in our next speaker, I'm pleased to introduce Sarah Stangebye from Georgia Institute of Technology. Field is in material science and engineering. Advisor was Josh Catcher, thank you. Residency was at Sandia National Laboratories in 2021. And again, characterizing plastic deformation mechanisms in metal thin films using in situ TEM nanomechanics. So the floor is yours.
Good afternoon, or good morning, everybody. My name is Sandra Stangebye. I was a graduate student at Georgia Tech. I defended back in March, so I think this might be my last chance to share my research with people, and I'm looking forward to it. I will be discussing how we've used in situ TEM nanomechanics to characterize and better understand the plastic deformation mechanisms that are active in metal thin films. So why do we care about how metal thin films behave? Well, they're used across many different microelectronics or microelectromechanical systems or MEMS devices. Basically, these are tiny sensors that are used across a wide range of industries. And as you can imagine, technology is getting smarter, faster, smaller, and so we need better and more reliable nanomaterials. Specifically, metal thin films are used as structural coatings or electrical contacts in these devices. And through the operation of the devices, these metal thin films are subject to stresses and strains and fatigue, which can ultimately lead to failure. So we need to optimize the mechanical properties of metal thin films. And one of the ways that we can do this is by changing the microstructure, and more specifically by decreasing the grain size into the ultrafine grain or nanocrystalline regime. This is because in a material, as you decrease or change the grain size, many different unique properties arise because of that. And most of these, or all of them, can be contributed to increasing volume fraction of grain boundaries, or the region between where two grains meet. The ones that we're most interested in, and possibly the most notable, is when you decrease the grain size in a metal, you will get an increase in strength. This is because in metals, plastic deformation and the strength is controlled by the slip of dislocations. Dislocations can slip, but when they reach a grain boundary, they are effectively blocked. So if you have more grain boundaries, you're going to get more blockages to the dislocations, which leads to an increase in strength following the Hall-Petch law. Unfortunately, accompanying this increase in strength is a decrease in ductility. This is for the same reason. If you prevent dislocations from gliding, plastic deformation can occur, and so your material is going to be more brittle. And so you see here that nanocrystalline metals, although they do have high strength, they suffer from limited ductility, which really limits their direct application. And then, in addition, nanocrystalline and ultrafine grain metals also show this unique increased radiation tolerance, which makes them a viable solution to radiation tolerant materials. Once again, this can be contributed to the high volume fraction of grain boundaries, because grain boundaries can serve as effective sites for the defect absorption. So you see near the grain boundary here, you can see that some radiation damage has been absorbed. So we want to understand how these materials behave, particularly under dynamic conditions or under mechanical stress. This is because under a mechanical stress, the mechanical properties are dictated by the deformation mechanisms that are active as we're pulling these materials apart. As I already mentioned, in the traditional grain size regime, so large grains, deformation is dominated by dislocation processes, so dislocation generation and slip. However, if we go to the opposite side of the grain size spectrum, where grains are in the size of nanometers, grains are no longer large enough to support dislocations, and so this forces the deformation to be dominated by grain boundary processes. So this can be grain boundary sliding, where grains slide on top of each other, or grain rotation, or grain boundary migration. In the middle here is where the ultrafine grain and the higher end of the nanocrystalline regime lie. And the deformation story is really quite interesting because it's a mixture of both of these extremes. We have dislocation-based mechanisms, such as dislocations emitting from grain boundaries, but also the grain boundaries contribute directly in the deformation through, once again, grain boundary migration, and et cetera. But it's not really well understood, all of these mechanisms and how they play together to contribute to the deformation. And it's not well understood what is the rate controlling deformation mechanism. So which mechanism is basically dictating how fast a material deforms. And not understanding this is really hindering material design towards exceptional mechanical properties. So that's where my project comes in. We take a three-pronged approach to try to fully characterize the deformation mechanisms that are active in these materials. The first portion is through microstructural characterization and observations of the mechanisms themselves as they occur in real time. The next portion is quantification of the mechanical properties, both through just measuring the stress and strain response, as well as measuring something called activation volume, which I will touch on in the next slide. And then finally, we collaborate with atomistic modeling group on campus, where they can go through and model individual mechanisms that we've identified in the TEM to try to build a full picture of what's going on in these materials. So as I mentioned, activation volume is one of the unique aspects of this project, and this is because the activation volume is essentially a signature parameter that's associated with a dislocation mechanism. This is because in order for a deformation mechanism to occur or a dislocation to glide from point 1 to point 2, it must overcome this local barrier. A portion of that barrier is provided by the mechanical work done by the applied load, and the remaining portion is the free energy of activation. So this activation volume is this V star here. It's really the relationship between these two mechanical and thermal components. It's helpful to use because it's a unique parameter that's associated with unique mechanisms. And I think this is visualized well in this plot here. Each of these lines corresponds to a different mechanism. And so you can see the activation energy versus stress, they have different curves, and specifically at the same activation energy level, so at the same experimental conditions, the slope of these lines, which is the activation volume, differs between these two mechanisms. So the idea is we could measure this and then get a value and hopefully relate it to atomistic mechanisms. Atomistic models are our friends in this case because they can generate these curves for us and help predict what value we'd be expected to see. So some numbers just to throw out there, very localized mechanisms like diffusion that involve only a few atoms at once are expected to have a low activation volume, anywhere from 0.1 to 1 B cubed, where B is the Burger's vector cubed, whereas other mechanisms that span a large volume and involve many atoms are expected to have a higher activation volume. Experimentally, I can measure this by doing stress relaxation experiment, where instead of just loading monotonically until sample failure, you load to a set point, and then you pause the loading and keep the displacement constant, and allow the stress to relax or the stress to decrease as plastic deformation is occurring. And then you quickly reload to hopefully around the same stress level, and you relax again, and you repeat this until you want to go home or until your sample breaks. And then you calculate activation volume V star using this equation shown here, which essentially uses the ratio of the strain rates of the second relaxation segment and the first relaxation segment, as well as the total increase in stress during your reload. And I conduct these experiments inside a transmission electron microscope using this MEMS device shown here. It's composed of a thermal actuator and 2 capacitive sensors. And so the basic operation of the device involves applying a voltage across the thermal actuator, and through resistive heating causes a shift in this central shuttle here, which causes a shift in the capacitive beam. So the capacitive sensors are composed of mobile beams in white here and fixed beams. And so when the mobile beams are shifted due to the applied displacement, it causes a change in capacitance of those sensors. So CS1 here is rigidly connected to the thermal actuator. So from CS1, we can determine the applied displacement. And then CS2 here is rigidly connected to the load sensor beam. This load sensor beam has a known stiffness. So by CS2, we can calculate the displacement of that load sensor. And then knowing the stiffness, we can then determine the force on our sample. My specimen is glued in between these 2 capacitive sensors, so it's basically the connecting force between this portion of the MEMS device and this portion. My samples are basically tiny tensile bars that I glue on across the specimen gap. Ultimately, from this device, I can get force and displacement of our sample and then can determine stress and strain. As I mentioned, I conduct these experiments inside the TEM, which uses electrons to essentially create an image of your sample. You can identify things like a grain or grain boundaries and defects, dislocations, and I conduct these experiments in real time in situ so I can video those reactions. And so here's kind of like a low level picture of what I do. So on the left is a video of one of the samples that I'm pulling apart, and on the right is the corresponding stress strain curve. So in these type of experiments, I can choose to do different type of imaging and analysis. I can choose to zoom in and focus on a few grains at once and characterize those grains, or I can do things like study crack initiation and propagation. And so over the course of the 5 years, I have fabricated many different samples to try to probe how the microstructure of these thin films changes and controls the mechanical properties. I fabricate these specimens in a clean room following the process shown here. The first step is optical lithography to define the pattern that I'm interested in. The next is deposition. I've mainly focused on gold and aluminum thin films, thicknesses ranging between 100 to 200 nanometers, since these are good model FCC materials. The next step for a subset of the specimens is irradiation. When I was at Sandia for my practicum, I took some of my samples with me and we irradiated it with gold ions. And then the last step is to release the samples or etch away some of the silicon to leave freestanding nano tensile bars. As I've mentioned, I've turned knobs in these deposition recipes and the parameters to try to create a large variety of microstructures. I've made materials with small grains, or I've made thin films with larger grains by annealing. I've made textured films, non-textured films, and as I've mentioned, I've irradiated some films to investigate how their radiation damage impacts things. So for the rest of this talk, I'm only going to focus on 2 of these subsets, specifically being as deposited or unirradiated gold versus irradiated gold. So the only difference between these 2 is one's irradiated and one's not. And the main difference when we're looking at their microstructure is you see the unirradiated films, the grains don't have many defects in them. They don't have very many pre-existing defects, but on the right you see this is the inside of a grain that has been, a grain from a film that's been irradiated, and you see there's a lot of black spots. That's all the radiation damage due to the ions. So now I will jump into some of my in situ results for the as deposited or unirradiated films. On the left here is just a monotonic curve, how we normally start characterizing the mechanical properties. You see that there's a portion of linear elastic increase, the specimen's yields around 500 megapascal, and then plastic deformation occurs, we have some ductility until eventual failure. And during these experiments, I have taken videos and images to characterize what deformation mechanisms are active. And I'll show just 2 examples here. In the center is an example of a dislocation and nucleating at this grain boundary here and gliding within this grain unimpededly until it's absorbed at this grain boundary. And so this is very characteristic for these materials. You get dislocation, nucleation, and glide until they reach another grain boundary. Another mechanism that we commonly see is grain boundary migration. So here's a case where these grain boundaries are migrating outwards, leading to a net increase in the grain size of this grain and a decrease in the grain size of the neighboring grain. Once again, this is typical. We do see grain boundary migration in these as deposited or unirradiated case. What happens after irradiation? Oh, and what is the rate controlling? So we have multiple different deformation mechanisms, but which mechanism is the rate controlling mechanism that's basically controlling the deformation, or basically controlling the mechanical properties? What happens if we irradiate? First, we see the monotonic response on the left, the irradiated now shown in pink. We see that we reach higher strength, but essentially no plastic deformation occurs, and the sample failed rapidly. So this is not all that surprising. It's well known that radiation damage causes embrittlement, and this is because the radiation damage now inhibits the dislocation glide. So here is a video that before I start, this is just a big grain where it looks very messy, and that's because it is. There's a lot of defects in it. And if I start the video, you can see changes in contrast within that grain. That's indicative of dislocations being pinned on a defect and then becoming unpinned, and it moves a little bit until it reaches another defect, and so on. So the dislocations are essentially just crawling through the grains, which leads to the observed increase in strength and decrease in ductility. This video here is maybe a little bit easier to see because there's fewer defects in it, but you can see that once again dislocations are caught on those defects. We also do see evidence of grain boundary migration in these films, which actually ended up being my favorite results of my whole PhD. And it did all come because I did the practicum at Sandia, and I just shoved some of my samples in the chamber and reiterated it, and it ended up being really cool. But in any case, here's a grain that I've outlined before applying any stress or any load to it. And this is the same grain after 28 minutes under stress. And so you see that these grain boundaries have migrated outwards and in their path have absorbed defects. And this continues. Here is a video where you can see towards the end, this grain boundary migrates outwards and it absorbs those defects, and it's effectively cleaning the material of these radiation damage. So it's healing the microstructure. And this continues until eventually you get to a point where you have a large enough region that can now support dislocation, unimpeded dislocation glide and dislocation-dislocation interactions that is similar to the unirradiated case. Once again, though, the question still stands, which is rate controlling? And so I've finished discussing how we characterize the microstructure and the TM observations, and so now I'll quickly go to how we quantify the mechanical properties through activation volume. And as a reminder, activation volume is a signature parameter associated with deformation mechanism, and I calculate it doing repeated stress relaxation experiments. And so here's data from one of the in situ experiments. On the left is the stress strain curve. It's piecewise because I've removed the relaxation segments and plotted them separately in this stress versus time. I'll quickly show just 4 relaxation segments and the activation volume values that I've measured for these relaxations being 34 and 44 B cubed. So it's just an example of one specimen, but I've of course repeated it and repeated it and repeated it until I have many different data points. And so this is all the activation volume versus stress data points that I have for the as deposited gold. First, we see that there is a stress dependence. As stress increases, activation volume decreases. And that's why over here in the averages, I've split it up based on the stress values. So what happens if we irradiate it? You can now just ignore the green and blue. Those are for larger grains. So if we just compare the gray data and the pink data, we see that across all stress levels, the activation volume is higher for that in the irradiated. You know, it increases from average from 25 to 57 B cubed and 9 to 22 P cubed. And so here are some of the trends that we've seen how activation volume changes. Specifically, we see that activation volume increases with radiation and activation volume decreases with stress. And any change in activation volume could signify a change in the rate controlling deformation mechanism. So that is how I've quantified, but those values by themselves don't actually mean much because we don't know what mechanisms they are associated with. So that's why we turn to our modeling friends that can model individual mechanisms. And that's what they've done. They've done some models where they can model, an individual mechanism. This is surface dislocation nucleation from the corner. And what they basically can determine is that the activation volume for surface dislocation nucleation would be around 20 B cubed. And they've repeated this for many of the different mechanisms I've observed. For grain boundary dislocation nucleation, they expect 40 B cubed. So this is helpful on its own, but once again, how do we relate that to what I measure experimentally? And in order to do that, you have to consider the differences between the experimental conditions and the modeling conditions. And one of the main differences is the grain size. Experimentally, our grain sizes range from 140 to 760 nanometers, but the models are done for a grain size of 10 nanometers. So we need to come up with a way to account for this grain size difference. And we've invoked this Conrad's model here, which basically relates the experimentally measured activation volume value that I measure with the activation volume locally for mechanisms inside the grain and mechanisms at the grain boundaries that the models determine. And so we can make some assumptions, and basically what this equation tells us is that the activation volume that is the sample level that I measure can be related to the local activation volume that the models determine by this square root of D, where D is the grain size. So basically what that says is that as grain size increases, square root of D will increase, you'd expect that the activation volume itself would increase as well. So now we need to relook at our data, as well as the data or the values from the models. So once again, the models showed that for surface dislocation nucleation, the activation volume would be expected to be around 20 B cubed. But this is the lower end of that activation volume because this is for the smallest grain size. So if we use the scaling factor, we're going to scale it up to experimentally relevant grain size. So we'd be expected that that activation volume would be scaled up to 76 B cubed if surface dislocation nucleation was the dominant deformation mechanism. So we can see that all of our data points is below this value, and so we can ultimately conclude that dislocation nucleation processes cannot explain the low activation volume values that I measure, and are thus not the rate controlling mechanism, which tells me that other rate controlling mechanisms with an even smaller VC are operating, such as mechanisms that include diffusion. There are defects a lot that lie along a grain boundary that can move by diffusion. So that brings me to my conclusion, which I will skip over because I'm out of time, but hopefully convinced you that in situ TEM nanomechanics is a great way to study materials. And then for acknowledgement, I'd like to thank my advisors, Dr. Piron and Dr. Katcher, as well as our modelers, and of course the fellowship. The fellowship was hands down my favorite aspect of grad school. And then what's next? I am sorry, I didn't go to an NNSA lab. I work at Raytheon in Dallas, working on R&D. I'm an R&D project engineer for radar systems. It's still defense-oriented, and I would not be surprised if eventually I came back to NSA labs. So with that, I'd like to answer questions.